This is Module 11, Lecture Notes 21. Today we're going to be talking about solutions, and you've probably heard people use the term solution in just a general sense, maybe in cooking or maybe with cleaning solutions or things like that. So I think you have kind of a background of what they are, but let's first do some vocabulary with solutions. So a solution is always made by dissolving one substance in another. And solutions are called homogeneous mixtures. Do you remember back in one of the first modules when we talked about homogeneous versus heterogeneous? A homogeneous mixture is going to be all mixed in, so the solution looks the same throughout. Okay? So when we're making a solution, the substance that we are dissolving, like let's say we're going to make some salt water, the substance we are dissolving is called the solute. And it's often a solid. It doesn't have to be, but a lot of times it is. And the substance we are dissolving the solute in is called the solvent. Okay? When the solute and the solvent are mixed together, you have a solution. Okay, one thing dissolves in the other. Okay, so let's talk about why salt would dissolve in water in the first place. So we just took salt, which is NaCl, and the salt was the solute, and the water was the solvent. Okay, so you need to be able to distinguish what is what when you're making a solution. Let's talk about why salt would dissolve in water in the first place. So salt is an ionic solid. Remember, ionic means you have a metal and a non-metal. Okay, so here I have some salt. If we could zoom in to a microscopic level to one of these sodium chloride crystals, you would see a bunch of ions held really tightly to each other. Okay, something like this. It looks a lot like what I have shown up here. And they're held to each other because remember, they're attracted to one another. The sodium is attracted to the chlorine by their charges, okay? Well, when water comes in, the water is going to push between these sodiums and chlorines, and it's going to pull them apart. Okay, so let's say we have sodiums and chlorines next to each other. The water molecule is going to come in and surround those and pull them apart from each other. Okay, now imagine you have a bunch of water molecules doing that all over the place. It's going to keep them from being attracted to one another, and thus it will stay dissolved. Over here in this picture, you can see that on a water molecule, you have two hydrogens and an oxygen. Okay, the hydrogens are positive, so they're going to be attracted to the chlorine, and the oxygens are negative, so the other end will be attracted to the oxygen. So water is the perfect substance to come in and dissolve an ionic solid because water has both positive molecules and negatively charged ones, so it can really attract to the bonds in the ionic solid. Okay, and it breaks it apart. All right, so dissolving ionic solids is obviously the most common. You might dissolve baking soda in water, salt water, lots of ionic solids will dissolve easily in water. But what about some other compounds? So what about a covalent compound, like something that is just made up of nonmetals? For example, like a carbon chain with just carbons and hydrogens. Okay, these do not dissolve well in water because they don't have any electrical charges between the atoms. Okay, there's no attraction between the carbons and the hydrogens. They're just sharing their electrons. They do not interact easily with water. An example of this would be Crisco. If you've ever worked with an oil or an oily substance, it is covalent and it does not dissolve well in water. Okay, polar covalent compounds like NH3 or ethanol, something that has a polar end to it, they would dissolve somewhat in water because of those small charges. Okay, so that's the difference between those two. Okay, so the things that you should be able to know from these two sections are that covalent compounds do not dissolve well in water. If you would like some other examples, oils, fats, those sort of things would be purely covalent. Polar covalent, you should know that they can dissolve in water, not super easily, but they can. And this would be alcohols like rubbing alcohol or gasoline, something like that, for a few other examples. Okay, we've talked about dissolving solids in liquids, which is the most common type of solution, like we did here with our salt water. But you should know that a solution is anything dissolved in something else. So I gave you a couple other examples so that you can picture it. If you took soap, which is a liquid, and dissolved it in water, which is another liquid, that would still be a solution. Okay, so liquids can make solutions. And what's really cool is that gases can make solutions too. So when you drink pop, let's say you have a bottle of pop, you actually have a gas dissolved in a liquid. Your carbon dioxide bubbles are a gas dissolved in a liquid. So that would also be a solution. Okay, with solutions, we often talk about something's solubility, and that just means how much solute can I dissolve in a solvent? How much? How much can be dissolved? So something's solubility means the maximum amount of solute that can dissolve in a given amount of solvent. Something that is very soluble, you can dissolve a lot of solute. And something that's not very soluble, you cannot. Okay? So if I take my saltwater solution, you might have done this before, but you can actually dissolve quite a bit of salt up to the point where the solution cannot hold anymore. You'll keep adding and stirring, and at some point, the salt just sits on the bottom. Maybe you've done it with Kool-Aid, and you've added enough that the solution becomes saturated. Okay, that is the point at which you have added the maximum amount of solute for the solution. That is called a saturated solution, and that is something you should know. Okay, there are ways to get more solute to dissolve, and we're going to talk about that for each of the three states of matter. All right, so we can put more solute dissolves when, and let's talk about some different cases for how we could get more of a solid to dissolve. Okay, so if you think about this, what could I do to the temperature to get more of my salt to dissolve? And I think most of you know the answer, that if I use warm water, I can actually get more salt to dissolve. So here in this first box, I want you to put for solids an increase of temperature makes more solute dissolve. Pressure does not have an effect on solids. Okay, for liquids, there's actually very little effect for temperature and pressure. But But for gases, we see a couple different things happening. The first one I want to show you is with pressure. All right, so I have a bottle of pop here, and of course, when they had the Purdue pop, I had to get that one. Now this has not been opened, so it is under high pressure. And I think you're familiar with the fact that when you open this, what happens to the bubbles? Do they stay dissolved or do they come out of solution? Okay, when I open a pop, many of the bubbles that were dissolved are no longer dissolved and they're coming out of the solution. So for gases, we're going to say that at a higher pressure, we have more solute dissolved. Increasing the pressure keeps more of our solute dissolved. And I hope the pop analogy will help you remember that. The bubbles stay dissolved under high pressure. Now, what about temperature? We can also relate this to pop. Does cold pop taste more bubbly? Or when you leave it out on the counter and it gets to room temperature, or even warmer than that, is it more bubbly? And I think most of you would say that at a lower temperature, it tastes like it has more carbonation. So more bubbles would be dissolved at a lower temperature. And maybe even down here you could write pop analogy for both of these to help you visualize those changes in temperature and pressure. Okay, so from this chart, you should just know how temperature and pressure affect how much solute can be dissolved. All right, so on the back, I'm going to walk you through a couple problems that you might see in this unit. Because a lot of this unit is talking about vocabulary and just thinking about how these principles relate to each other, you're going to see more thinking questions. So let's work through a couple together. A student needs to dissolve 50 grams of potassium chromate crystals. Okay, this is an important word because it tells you that the student is working with a solid. He's trying to dissolve a solid in water. He's having a hard time getting all of the solid to dissolve. He is not allowed to add any more water. What should he try to do to make all of it dissolve? Okay, you could go back to our table and look at the solid and see what the student could do to increase solubility. So we could put that he could try heating the water, and likely using warm water, more of the solute would dissolve. Okay, next one. A chemistry lab is storing several bottles of solution made by dissolving methane gas into octane liquid. So we have a gas trying to be dissolved in a liquid. The chemist noticed that every once in a while the lids from the bottles pop off. She thinks the lids pop off because the gas is escaping from the solution, a lot like our pop bottle. What can she do to stop the lids from popping off? I'd like you to think about this, write a thoughtful answer, and then come back and check. Okay, so from our chart, you can see that gases can be affected by both temperature and pressure. So you could have wrote something about either one of these. You could say that they could decrease the temperature of the room. And that would likely help some of the gas from escaping. Or they may need to increase the pressure of the bottles. Okay, so as long as you've mentioned both the temperature and the pressure, or one of them, you will have covered that question. Okay, lastly, in this part of the unit, we're going to touch on energy changes that happen when making solutions. And we will come back to both of these terms in a later unit, but I just want to introduce them to you now. Oftentimes when you make a solution, and you're mixing your solute in your solvent, and you feel the outside of your container, you might notice a temperature change, okay? An exothermic process is a process that releases heat, and you're gonna feel that it's hot. One of these that I can give you an example of is Drano. Okay, the stuff you pour down your drain to open your pipes. You may have had experience with this before, but whenever you use Drano, the solution gets really, really warm. And that's why it can be somewhat dangerous, but it actually releases heat when it is mixed with water. An endothermic process would be one that absorbs heat. And so it's going to feel cold to the touch. If you've ever had one of those cold packs that's in a first aid kit, it's like in a box and it says like smush the two contents together, and you mix them and it gets cold. That is a solution that is endothermic to make a cold pack. Okay, so those are just two examples, and we will come back to those two terms in later units. Thanks, guys.